Today I'm going to tell you about part of the procedure for finding enough elements of the arithmetic group in order to arrive at some conclusions. So I remind you that we already worked out a division algebra. We found a concrete version of it. We're interested in a certain arithmetic subgroup. We know how to work out, concrete conditions that say when an element would actually be in the multiplicative group of D belong to this subgroup, and then somehow we find a few elements of the group. Now, that step I am not going to discuss, but as in one of Donald's talks 2 days ago, it involves a computer search. You look through many possibilities. So the set of elements that we find is called A. This is not usually a very big set. I think normally we only found it ended up being 3, 4, 5, 6 elements. For the calculations that I'm going to discuss, we're not really interested in all of the algebra that's involved in D. We're just going to treat these elements as matrices in PU21. So actually, they're already given as matrices. Our concrete realization of D is as a matrix realization. In order to convert to matrices in PU21, well, first of all of those algebraic expressions need to be rewritten thought of as simply as complex numbers. Also, in the case that the base field of everything K has a is of order 2 over Q, we have to choose the correct sign for the square root of B. We arrange so that for one sign we're going to get PU21, for the other sign PU3. We want the PU21 sign. And also the form that will be preserved is not the standard form, so it's quite convenient to conjugate by some matrix to get it into the standard form. And then this set of elements that we have becomes a set of matrices in U21 in the completely ordinary way. And I did the calculations that I'm about to describe using floating point arithmetic. So I've just dropped all the algebra. Donald did more or less the same calculations, leaving everything in much more symbolical form, and this was also possible. But so if by chance you didn't understand the algebra very well, this lecture is independent of that. We just need matrices in PU21. So to measure size of elements, we look at a particular point in the ball, the origin. This is an arbitrary choice, of course. One could use any point as the origin, but use 0 as the origin. And we call the size of an element is measured by how far it moves the origin. Okay. So it's not the same value, but if you just want to know what's bigger or smaller, this is the same as looking at the Hilbert-Schmidt norm of the matrices. Okay. So I believe Donald mostly just looked directly at those Hilbert-Schmidt norms, but it doesn't make too much difference. Now, in the case that Cartwright explained, I've made another date area. The day before yesterday, he showed a particular case where he had a neat method for finding the elements of gamma bar in order of their size. But that particular method is not usually available, and usually we get these elements A, but we have no idea whether they're the smallest elements or not. Maybe one of them is one of the smallest elements, but the next one isn't. So we just have elements in gamma bar. So what we want to do is to generate lots of elements in gamma bar. And how do we do it? Well, we can always look at inverses and products of 2 elements. But since the group is infinite, if we just decide to generate more elements by doing this, we will just keep getting more and more elements. We never, we never end. So this is what I actually did. And I believe that Donald wrote a more or less a very similar program, which I think did more or less exactly the same thing. So we maintain a list of the elements we've found so far. We start out with the elements A, and throughout we keep this list sorted by size, this size, how far it moves the origin. And we fix an arbitrary limit for how long we'll let this list be. So now, then we start multiplying elements, and whenever we find a new element, we insert it in the list in the proper place. And it may be that the list is full, and if that happens, we drop the last element in the list. So we're always keeping the smallest n elements that we've found. Okay? Now, at a certain point, all possible new elements, that is, all products, have a size that puts them beyond the length of the list. So then we're not going to be able to put anything more in, and so that's when it stops. So how do we know that the algorithm terminates? Well, that's because we do know that our group gamma bar is discrete. Okay? If the group was not discrete, then we could easily keep going and finding smaller and smaller elements. But no, well, the group is discrete, so it will terminate. Okay? Here's a detail. I'm sure that the program could be written to do exactly what is said here, but what my program actually did is not to do this one element at a time. It generates batches of new elements, and then every once in a while it merges that batch with the old list and sorts it, drops the largest elements. But it amounts to the same thing. I don't know if Donald's program does it in exactly the same way, but this is the principle. So our hope then is that we are getting, that with this system we're ending up with this, what are in fact the smallest elements in the group, the capital N smallest elements in the group, more or less. Whoops. Okay. So more precisely, if S prime is the set of elements in the final list, let's choose some limit which is a little bit less than the maximum value. Okay? And let's look at all elements, or that is less than that, which in our list which are no bigger than that. And so that set is going to have the following three properties. Naturally, the elements are going to be small, distance less than R1. It's going to be closed under inverse. Well, that's because in this diagram here, I can just change the labels. In orange translating, you see that the distance from O to G of O is the same as the distance from O to G inverse of O. And this is the most important thing. If two elements are in S, and if this distance is less than or equal to Rn, that's also going to be S. So why is this? Well, when we were trying to work out all possible products, we worked out, in particular, the product of G of H. And its distance is there, and since R1 is less than this maximum value, we would have dropped off the last element of the list and used this one instead. So it has to be there. So, so this means that S satisfies a sort of peculiar version of the group property. It's closed under products, but within that size. Okay. Now, so I no longer care about A. We'll just work with S. And also, let gamma be the group generated by S. That's in gamma bar. It may or may not be true that gamma is equal to gamma bar. We will check that later, but for the purpose of this talk, I don't even need to care about gamma bar. Let's just work with gamma, the group generated by S. Oh yes, and I remind you that there was another group gamma in these lectures and in Prasad and Jung's paper, and this is a different one, but I'm using the same notation for two completely different things. Okay, so of course this is what we hope. We're hoping that we have in fact found exactly all elements in the group whose size is less than or equal to R1. But is that true? And if it is true, how can we prove it, right? There's nothing in what I said that, that proves that that is so. We would just like it to be so. And what I've said is, I've explained how you can get an S with those three properties, and I've suggested why one would like that to be true, but how can one, how can one be sure? Okay, so for these purposes, we generate a sort of Dirichlet fundamental domain, but it's not quite the Dirichlet fundamental domain for gamma because we just deal with the elements of S. Okay, we don't have all the elements of gamma. We're not even sure whether we have all the small ones. So this is just relative to S, the Dirichlet fundamental domain. So this is a subset of B of C2, which consists of things that are closer to the origin than to any translate of the origin by elements in S. So that's why I call it FS instead of just calling it F for fundamental domain. Now, R0 is this maximum. It's the radius of Fs. One advantage of this room is that I can draw a picture here. So here's the origin. Of course, this is really in two complex dimensions, not two real dimensions. And here is Fs. It might look something like this. And this distance here is R sub 0. It's the largest distance. Okay? So the radius. Okay? Now, it is important that R0 can be calculated as a number. If our set S is made up of concrete numerical matrices, we can also calculate R0 this way. Now, I would like to point out that elements in S which are as big as that, bigger than twice R0, don't have any effect on what Fs is. Why is that? Well, supposing we want to look at the elements in Fs which lie along a certain geodesic. Now, according to this picture here, I find that if the distance from z to g of 0 is less than the distance from z to 0, then the distance from z prime to g of 0 is less than the distance from z prime to 0. And why is that? That's because I'm thinking of this as a geodesic. So this distance is smaller than that one. If I go to z prime, relative to the origin, I just add that much. And relative to g of 0, I add no more than that much, so it remains true. So this means that an element of this element g of 0 by itself will allow this much inside Fs, but nothing beyond. It will, so this Dirichlet fundamental domain, as usual, is going to be, star-like. Okay, so supposing that I have an element G with a G of 0 bigger than 2R0. Okay, so this would be G of 0. And you ask, where, if anywhere, is the point where these two distances are equal? So this would be the point where the condition given by G of 0 forces us to be outside of the fundamental domain. And since this distance is bigger than 2R0, we see that this distance must be bigger than R0. And that explains this last comment. So the condition given by this G of 0 is not, in fact, adding anything to that comment. Now, of course, it can turn out that R0 is infinite. Perhaps gamma isn't co-compact, so it wouldn't be all of gamma bar. It wouldn't even be finite index in gamma bar. Another possibility is that things aren't working out because my choice of R1 was too small, probably because my n was too small. And yet another thing that might happen is n might have been so small that I didn't really end up getting all the elements. I see that there's I'm missing something there. Okay. So the first possibility can certainly happen. In fact, it did happen in a couple of cases. And the reason for that was just that the original set A wasn't really a generating set. And if that happens, then this group is most likely not co-compact, and so nothing was going to work. So we can, so it's a quick criterion for success is at least R0 has to be finite. But whereas for these other two things that can go wrong, well, you can try to correct it just by doubling n and trying again. And in fact, this always worked for this project. Now, obviously, the fundamental domain can be compact only if gamma bar is co-compact. So a question which really springs to mind is there some way of adjusting these methods to be able to deal with non-uniform lattices, not co-compact, to somehow deal with the cusps? This is not such an easy question. Certainly no obvious answer comes to mind, but it could be very useful if there was such an, way, if there were ways of doing it. Okay, so for the rest of the talk, I'm going to go through the proof of this theorem from that paper, and this is a theorem which will tell us that, in fact, our set S is big enough. So for this, you don't need to remember exactly how I got S. S is going to be a set with the following properties. The sizes are all less than or equal to R1. It's closed under inverses. It's finite. And if I have two elements in there, their product will be there so long as the product is also of the right size. This is my only condition on S. Gamma, as before, was this group generated by S, and let this Fs and R0 be as on 2 slides ago. And we need this condition. R1 has to be bigger than 2R0. Okay? That little discussion over there gives a small idea of why 2R0 is exactly what we want. Okay? Okay. So in that case, we really can say that S is made up of the elements in gamma whose distance is whose size is no bigger than R1. We can also say that if we make a presentation for our group using the elements of S as generators, or more correctly, symbols corresponding to the generators of S, and if we use true identities of this form as relations, then this gives a presentation of gamma. Okay, so now that last bit sounds, it's the same conclusion as in the theorem of Macbeth, and in fact, that theorem there is very closely related to the theorem of Macbeth. I mean, it's the same idea, which, as was mentioned, is an old idea, very old idea. Here's the difference, though. In Macbeth's theorem, the set used in place of S would be this one. Okay, everything which shifts some x so as that it intersects itself. And in order to identify that set, you'd really have to know what all the elements of gamma were. Okay, as in the talk that we heard, they did know them. Whereas our hypothesis in S can be checked just looking at S itself. We don't have to know all of the elements of the group. Okay, that's why this is not a seriously new idea in any way, but that's why there's something new in this version of the theorem. Now, by the way, if one was trying to apply Macbeth's theorem, then what would X be? Well, X would be could be that fundamental domain, but let's probably more simply just take it to be the ball of radius R0. Okay. Now, you will notice in the proof that there's very little about the geometry of B of C2. We're not even using the fact that the curvature is negative, so I believe that all we need to use is that it's simply connected, that's as in Macbeth's theorem, and that it's a geodesic metric space. I don't believe one uses anything more than that. Okay, so all the rest of the talk, we're going to assume the hypotheses of the theorem. And here's the first lemma. Gamma is generated by S0 and those, which is those elements of S which are at distance no more than 2r0 from the origin. So at least for having a generating set, we don't need to use all of S. We can just use these elements that are at no more than 2r0 for size no bigger than 2r0. Okay? Now, I will now stop using the computer. Now, normally when I stop using the computer, it's because I didn't have enough time to prepare the rest of the slides. But that is not actually the case today. The case is that this theorem is, nicely written up by Donald in that article, and if one wants to go through it carefully, one can find it there. On the other hand, it's the sort of theorem where there are a lot of pictures, and it's certainly a lot easier to draw these pictures on the blackboard than to try to duplicate them. I mean, easier for me, but also easier for you, I think. And consequently, I press the power button. Okay, so my objective was to prove that gamma is generated by S0, which is to say it's generated by elements of S that are that have size smaller than 2r0. That's the objective. Okay. By definition, gamma is the group generated by capital S, so we just need to show that capital S lies in here. So what I'm going to do is I'm going to take G and S. By contradiction, I'll assume that G is not in the group generated by S0, and I will assume that that's the minimum possible distance. Okay? Now, see? Yeah, see. There's no trouble with having minimum distances because one of the conditions on S is that it's a finite set. So I look at the geodesic from O to G of O, and I choose this C, which is just a little bit beyond the radius of the fundamental domain, and therefore C is outside the fundamental domain, and therefore there is some element of S which is closer. Okay? So this element is, H of 0 is closer to there than 0 is. Okay. Now what do we know about H? Well, H is also an S, probably. The distance from H of 0 to C is less than the distance from 0 to C, which is therefore less than or equal to R0 plus epsilon. And from this, we can draw the obvious conclusion about the distance from 0 to H of 0. It's no more than this plus that again. So it's no more than twice R0 plus epsilon. And from that, we can deduce that it's less than or equal to 2R0. Okay. Now, why can we deduce that? Well, that's because of my choice of epsilon. Yeah. Again, S is a finite set, so I choose epsilon so that if your distance is less than or equal to 2R0 plus epsilon, you have to actually be less than or equal to 2R0. Okay? Which implies that H is in S0. That's what we know about H. So now I want to consider let's see, how did I express this? I expressed it as H inverse G. Is this a good way of thinking about it? Yeah, let's consider H inverse G. So translating the whole diagram, I could translate this so that this was at 0 and this was H inverse G of 0. And so if we look at the distance from H inverse G of 0 to 0, this is less than or equal to the distance from 0 to G of 0. Now, why is that? Well, the distance here was smaller than the distance there. If you go from 0 to G of 0, you're continuing a geodesic. Here, you're not continuing a geodesic, but that just makes it smaller. So, in particular, it's less than R1. Okay? So this means that H inverse G is a product of two elements in S of size no bigger than R1, and consequently, we can deduce that H inverse G is an element of S. Okay. Let's see, is that what I wanted to say? Yes, that's what I wanted to say. No, uh-oh, I'm panicking. That's certainly what I want. I mean, that's certainly what I wanted. And it follows that the distance from C to dear me. No. H inverse G is an element of S, which yes. Yeah. This is all I want to say. H inverse G is an S0 because we choose G and S minimal outside, not S0, but the group generated by S0. That's all. That's all. But this distance is actually less than this distance, so this has got to be an S0. But if you look at H is also an S0, and so if you have this and that, then in fact G would be an S0 contrary to our hypothesis, and the thing is proved. Okay, so if one actually writes it down as I just did, it's a little fiddly and you have to think about it, but this is actually the standard argument that you use in the proof of the first part of Macbeth's theorem, or whenever you use that sort of argument. The only thing that's different about this is that we had to be careful that all of our distances were small enough so that we could actually be sure that H inverse G was in our set S. Good heavens. So Lemma 2. So choose epsilon 0, which should be less than or equal to R1 minus 2R0 over 2. It turns out that this is what's needed. So if the distance from O to Z is less than or equal to that, R0 plus epsilon 0, then there exists G and S with the distance from G of 0 to Z less than or equal to R0. Okay? So this is the usual fact about the Dirichlet fundamental domain, that if its radius is R0, then every point of the space is within R0 of some translate. The only important point here is that here I can be sure that G is an S. This is reasonable because, well, why is it reasonable? It's because from 0 to z, that's no more than R0 plus epsilon 0. Epsilon 0 is small, and just because of the way fundamental domains work, we would expect to be able to find this g of 0 at distance less than or equal to R0. And if that is true, then the distance from O to g of 0 is no more than 2R0 plus epsilon 0, and therefore it ought to be in S. So it's again the usual thing. We just want to make sure that we're actually getting an element of S and not just some other element of the group that we don't know about. Let's see. So what's the proof there? Well, okay, here's the origin, geodesic to Z. This distance here is less than or equal to R0 plus epsilon. And here is, let's see, g of 0, where I make the choice which should work the best. I want g to be an S, and distance from Z to G, distance from g of 0 to Z minimal. Okay? If that one works, then we're okay, and if that one doesn't work, then we failed anyway. So since this distance has to be less than or equal to that distance, also this distance is less than or equal to R0 plus epsilon. In case anyone's wondering, there's no particular reason that g of 0 can't be 0 itself, but I don't draw the picture that way. Okay. Now I translate this whole picture by g inverse, so I'll put in the other labels in orange. G inverse of 0 here, g inverse of z here, and 0 here. Okay. Now, if this distance is already less than or equal to R0, then we're already done. However, if it isn't, then using the orange labels, we see that there has to be some other translate of the origin, h of 0, which gets us even closer to z. That's because of the previous lemma, where here we have also h is in S. Okay. So when this happens, this is even smaller than that. So that's less than or equal to R0. Yeah, I can assume it's less than or equal to R0. Okay, so now what would the white label be here? I would have to multiply by g. It's gh of 0. So we ask, what's the distance from 0 to gh of 0? And we see that it is no bigger than that plus that, which is 2R0 plus epsilon. Distance from O to gh of O is less than or equal to R0 plus epsilon plus R, epsilon 0. It should have been epsilon 0, which is less than or equal to R1. So gh is something which could be an S, but it's also the product of two elements in S. So again, using that closure under multiplication, if you don't go too far from the origin, we discover that gh is in S. And But this contradicts my choice of G and S as the one that makes the distance minimal. And now I have another element of S which is even closer. Okay? But in any case, you just see from the picture that I have this where for G I have to use GH. Okay, there's very little to that. So now we proceed to the proof of the theorem itself. Let's let G be equal to y1, y2, yn with yj in S0. Okay? According to that first lemma, any element of capital S A of gamma can be generated by elements in S0, and suppose as well that the distance from the origin to G of 0 is less than or equal to R1. So what we need to do is to prove that G is already in S. And for this, life is a little more complicated. So let's see. First of all, let Gj equals y1 through yj in order that we will have that Gj, yj plus 1 is equal to Gj plus 1. Right? So partial products. And then I need the following diagram. This is a real two-simplex. And I'm going to construct a map of this from into the ball. Whoops. And the idea is that the boundary of this is going to correspond to this relationship here, right? So I'll tell you first where these vertices should go. This should go to the origin. This should go to G1 of the origin. This should go to G2 of the origin, G3 of the origin, G4 of the origin, G5 of the origin, and G6 of the origin, which should be just G of 0 because I have chosen n equals 6 because this is the smallest number that makes it clear what the diagram is. Okay? So these vertices are going to be going in like that. In fact, in this first diagram, I probably do better not even to draw the rest of this. Whereas, okay, and now I will tell you how to define phi on the boundary. And the answer is that in each case, I use a geodesic. Now, let's see. Just geodesic, and also here I will want to use a geodesic. Okay, that's how I fill in phi on the boundary. Each is a geodesic. Whereas in here I just fill in. Okay. I want to map this into B of C2. I fill in using, of course, the fact that that's simply connected. Now, subdivide into smaller triangles so that the diameter of phi applied to a small triangle is less than or equal to epsilon 0. Okay. So this bit can be understood independently of the rest. I mean, independently of exactly what I was doing. All I need is that phi has a map, that the triangle has a map to be of C2, and then I make a further subdivision, like this, say. You know, not just there, everywhere. So that every small triangle is mapping into a set with that diameter. So this is just uniform continuity, of course. Okay. And now, on this subdivided thing, I am going to make the following. I'm going to make a series of choices which are as follows. We're going to have, if this, say, is a vertex, and that's an edge, that's another vertex, directed edge, we will choose. I haven't done it yet. We'll choose x of v1, x of v2, which are elements of the group, and also a y of the edge, which is going to be an element of the group, in such a way that x of v1 is equal to x of v2 is equal to x of v1 times y of the edge. That's a directed edge. Okay, so the idea then is that for these elements here, I am just going to choose the identity G1, G2, etc. But for all the other elements, all the other vertices, I have to proceed in the right order. And there is something I want, though. I want this x of v to be sort of an approximation to phi of v. We'll have that the distance from x of v at the origin to phi of v is less than or equal to r1 halves on the bottom edge, on the bottom side, that is, not the bottom side of every little triangle, just this bottom side, and otherwise it's less than or equal to r0. So this is the sense in which my elements x are giving me a sort of approximation to the map phi. So how do we do this? Well, okay, consider a side here that's maybe going from xj to from gj to gj plus 1. We actually chose our map so that that distance, this is vj plus 1. We have that phi of vj plus 1 is exactly gj plus 1 of the origin. That's the way we chose it. And phi of vj is exactly gj of the origin. That's the way we chose that. And then we've divided this up, remembering that this is a geodesic of size, of length no longer than the distance between these two, therefore no more than r0. What we do is we set it to gj here and gj plus 1 here. If we divide it into more than 3 parts, well, up to halfway we use gj, up to the other half, and then we start using gj plus 1, and we're never further than, whoops, r0 halves. So the labels on the edges come out like here. should use a different color. Labels on the edges come out, whoops, but not that one. Edges come out like this, that this one is going to be 1, this one will be yj, and this one will be 1. And if there are more things, it's a bunch of 1s, and then a yj, and then a 1. That's what we do along here, whereas along the bottom edge, again, we've already chosen the values here and here, which are supposed to be the identity, and G, again, this is a geodesic, and now its length is less than or equal to R1, so if we divide it in 2, that's less than or equal to R1 halves, and what we do is we use 1s up to the halfway point, and then G's up to here, and here our edge labels come out as 1, 1, 1, 1. This edge label comes out as G. No, it's G inverse. So I'm drawing these in the wrong direction. Not that it makes a great deal of difference, but yeah, G there, and then 1, 1, 1, 1. Yes? Okay, and we match that. Now, I say to do this for all the vertices of the triangle, but so far I've only told you what to do along the boundary. So for the rest of the triangle, we have to generate these things one at a time. And we're going to be generating them always working left to right. I mean, one could choose other orders, but supposing we know the value here, we're going to choose the value here, and then the value here, then the value here, up to a certain point. Always working from left to right. Now, let's see. Oops, no. So, supposing that we have V here and V prime there and this edge here, and we need to find, we have that x of V given, known, and we want to calculate x of V prime. So the question is, how far is V prime, no, not from that. X of 0 to V prime, to phi of V prime. Got to get this right. X of 0, 0 to phi of V prime. How big is that? Well, from x of, whoops, no, not x of 0, 0. What am I saying? Here's what we do. Inside the ball, this will be the ball. Here's x of V of 0, and not too far away, that is not going to be too far from phi of V. And then phi of V prime is going to be even closer to phi of V. And my question is, how far is this distance? Okay, and the answer is that this is less than or equal to R0 plus epsilon 0. Now, why is that? Well, from here to here, it's no more than R0. That was my condition. If this isn't the bottom edge, but we're never going to be doing this on the bottom side. I've already assigned them on the bottom side. And then this from here to here is no more than epsilon 0 because I've chosen these edges small. So this thing is actually not so big, and that's the same as the distance from 0 to x of V inverse phi of V prime, which implies that there exists y of, this is what we'll use for y of the edge, such that the distance from y of the edge times 0, this would be an s, to this x of v inverse phi of v prime is less than or equal to r0. Okay. So, and that was what that second lemma said. And this means that if we then make the choice that, so that x of v prime is equal to x of v times y of the edge, then everything's all right. I have that the distance from here, well, from phi of v prime to x of v, y of the edge, evaluated at 0, to phi of v prime, it's small as it should be, and also y of the edge is an s. And let's see. No, that's fine. Okay, that's actually important. I want it to be clear that y of the edge is an s. So let's see. Let me explain then how this has gone. I'm just going to do it in this case. So blue is supposed to correspond to y of an edge being an element of S. Okay? Now, if we look along these two sides, this is all in there. If we look along the bottom, the y's were 1 here. Everywhere except there it was known. And then for these others, we need to work left to right. So in this case, the smallest possible case, there's actually only one other thing to fill in, which we fill in working left to right here. That one is in S. All right. Now, I will now state one more lemma, which is that oops, 7, 8. I've locked. Yeah. If we're looking at an edge, V1, V2, edge, that the distance from x of v of 0, comma x v1 0 and to x of v2 of 0 is always less than or equal to R1. Okay. So why is that true? Well, again, here's x of v1 of 0, x of v2 of 0, they are respectively close to phi of v1 and phi of v2, which are close to one another. The only question is how big can these be? Well, except on the bottom edge, the answer was, and so I'll use v2, less than or equal to r0, and here it was less than or equal to r1 halves only if v1 is strictly on the bottom edge. And when we sum these up, we've actually chosen epsilon 0. This is less than or equal to epsilon 0. We've chosen epsilon 0 small enough so that this will be true. Okay. Moreover, well, so that's yet another tricky little lemma. On the other hand, this one is easy. If we have a triangle like this with y1, y2, y3, just because of the way everything is defined, y1, y2, y3 equals 1. Now this means, putting these two things together, in this triangle, whenever two of the edges have y's in S, then also the third does, right? If two of the things are in S, the third one is just the product of those two. It's inverse. Moreover, we've managed to set these things up so that the distance, this is the same as distance from O to Y of edge of O. We've managed to set things up so that our y's, so that these distances are minus or equal to R1. So once again, we can use the fact that S is closed under multiplication as long as you don't get too far away from the origin. By the way, well, okay, I won't say that. So looking at this diagram, these two are already in S, so that one will be an S. And these two are an S, so that one will be an S. We can just fill in, see? These two are an S, that one's an S. These two are an S, that one's an S, and as the final step, that one's an S. And this is the one that corresponded to G. So G is actually an S. Okay? Now, for those of you who have ever looked at the proof of Macbeth's theorem or any of the similar arguments that have been used for a very long time, you know that essentially this same diagram is also what you need to do to show what I said about the group being presented. It's presented with generators, which are just the elements of S, and relations, which are just the relations around the smaller triangles. And that produces any relation that goes around the larger triangle. This is, I believe, explained in that archive paper. It's certainly explained in Macbeth's paper. We could just refer to Macbeth's theorem from this point on. The bit that wouldn't be in Macbeth's paper is what I've just arrived at, that we can actually be sure that G itself lies in S. Okay. So I've gone over a little over, but
You have 2 minutes more.
well, let's call that going a little over. I've gone minus 2 minutes over. Well, it's always a sort of a mistake to present a proof, but there it is.